Okay, so let's just do a quick exercise to check our understanding of this thing. Okay, so remember the sampling distribution will come from a normal distribution with mean mu, which is the same as the population mean, and standard deviation sigma over the square root of n. So the population standard deviation divided by the square root of n. Okay, so let's say, all right, so our population will be IQ scores. Okay. There's a lot of debate as to the merit of IQ scores, but let's just say the population has mean this, mean 100, and standard deviation 15. All right, you take a random sample of 10 students. All right, what is the probability that the average IQ of these 10 students is over 105? Okay. And okay, so figure that answer out and compare that to what is the probability that a randomly chosen student has an IQ over 105. You'll need your calculators and z-tables to do this. Hmm?
That's the one thing I don't have.
One thing, do you need to borrow
My calculator.
a calculator?
I think it's 15 next to the 100.
That's the standard deviation
Okay.
of the population.
Okay.
Okay. So this is mu, and this is sigma. Let's make that right. Ooh. I'm sorry. That's always, I've been doing this for years and I still cringe every time you learn how to hold the chalk, but sometimes it still gets you.
the stuff I need to do.
Oh, did you?
I might have. I don't know where I got it. If you could check.
This, or? I
Yeah,
don't
no.
think so.
If you it right quick, I can just. No, it's fine. You can use it. Thank you.
I forgot to bring my stack of extras.
Actually, do you have a text? Usually use one. I have my text. I'll do it. Yeah. Thank you.
Okay, are you guys still working or good? Okay, so we'll do this one. Draw a random sample of 10 students. What's the probability that the average IQ of these 10 students is over 105? Okay, well, according to the central limit theorem, which we can use because the population is normal and we randomly selected our people. Okay, so according to CLT, what am I saying? Okay, the distribution of y bar has a normal distribution. The mean is still 100, but the sampling distribution is going to be 15 over the square root of 10. Okay, and I want to know what's the probability that we're over 105. Okay, and here my mean is 100. So my z-score is going to be 105 minus 100 divided by 15 over root 10, and I get I get positive 1.05. That's what I got, I think.
Do you need to calculate that?
Yeah, if I'm doing this, yes.
Sorry, is that says 105?
Yeah, 105
Okay.
minus 100 divided by the square root of 15 over the square root of 10. Okay, and that difference turns out to be 1.05 standard deviations. Coincidentally, 1.05 standard deviations away from the mean. Okay, so I look that up in my z table, and I get 0.8531, and so that means over here I have 1 minus 0.8531, which is equal to 0.1469. Okay, equivalently, I could have just looked up negative 1.05 in the z table and gotten 0.1469 directly. Okay, and over here, so what's the probability that a randomly chosen student? So now we're just dealing with individuals. So I could treat my sample size as 1, or I could just say I'm drawing from the population. Okay, it's the same thing. So now I have normal distribution 100, standard deviation 15. So my z-score here would be 105 minus 100 divided by 15. I get a z-score of 0.33. And when I look that up, so mean 100, 105 is right there. And I look up 0.33. The number to the left is 0.6293. And I want the greater part, so I do 1 minus that. And I get 0.3707. Okay, and again, alternatively, I could have looked up negative 0.33 instead and have gotten 0.3707 directly. So this is a review of last week's homework, and then here we just added one little element where we changed the standard deviation to 15 over the square root, or to sigma over the square root of n. Okay, and that's when you're dealing with means of a sample. So individuals is just the plain old normal distribution. Random samples, where you're dealing with the mean of that sample. Now you've got the central limit theorem. Okay. So this is all fine and dandy. So this is what we have learned in the theoretical land, and we are going to do our first practical application of what we just learned. Okay, this is chapter 6. We're going to just cover the first half of chapter 6, which is confidence intervals. So, in chapter 5, when we did the sampling distribution, okay, and I know, oh, so just an aside, last week we covered the normal approximation to the binomial. That actually is built out of this sampling distribution stuff, okay, and it's the idea that if you just have your distribution is just a yes-no distribution, okay, so it's either 1 for yes or 0 for no. If you take a large sample from that, it becomes like a binomial distribution, and that which ends up being it's kind of like the central limit theorem where you can approximate it with a normal. Okay, so you can reread the intro to that section, and it might make more sense or not. Okay, but anyway, so confidence intervals is our first practical application, because when we talked about sampling distributions, we said this is what the population looks like. It has this mean and it has this standard deviation. Okay. In real life, we almost never know what the population looks like, okay? Because we can't study the population directly. The whole idea of statistics is that we can't study everyone, so we study a sample, and we're hoping our sample represents the population. Okay? So let's say you randomly selected some people, and you studied these people. You know, what will your sample say about the population? Okay, and this is our kind of our first step here. Okay, so with a confidence interval, the idea is we do not know what the population looks like. All right? But we have a sample. So let me just, so we don't know what the population looks like. This means mu and sigma are unknown. Okay, but we have a sample. We have a sample, and we can study our sample. Okay, so from our sample, we can find the sample mean. We can find the sample standard deviation. Okay, we have a sample. We can study our sample. So we do know y bar, standard deviation s, and so these are properties of our sample. From this, can we say anything about our population? Okay. And in our class, we're only going to learn statements about mu. Maybe at your second statistics class, you'll learn how to make statements about sigma. Okay, but for now, we're just going to make statements about mu. Okay, so from our sample, can we make any statements or conclusions about the population? Okay, and specifically about mean U. And then one key assumption is that the sample we have is randomly selected, okay? Key assumption, sample is randomly selected. And we will say n is sufficiently large. So key assumptions.
Question.
Yes.
Why is the notation different? Like y bar, that's just a different.
Yeah,
like,
to
between...
distinguish between means and standard deviations from a sample and means and standard deviations of a population. For samples we use Latin letters, for population we use Greek letters.
Oh.
That's just tradition. Okay. So yeah, so the properties of the population are unknown to us, okay? And just the stuff we did earlier today, we pretended like we knew what the population, or I mean we said we knew what the population looks like. But in reality we don't, okay? So if that's unknown, but we have a sample that we can see, what does this tell us about the population, okay? So just imagine you've selected 10 random people, okay? You have no idea what the mean IQ score is, but let's say you got these 10 people, you get IQ scores, random IQ score, the IQ scores of these 10 people. Okay, the average turns out to be 96.4. What does this say about the general population? Okay. Well, we're expecting the average that we observe to be kind of close to the general population mean, but we really don't know too much, okay? So put that thought on hold, okay? And I'm going to tell you a story. Not a story. I will not tell you a story. All right, let's look at this, okay? All right, this is a picture. I'm drawing the picture here, and what is it a picture of? It's a picture of a dog. Okay, and the dog is going for a walk, okay, on a football field. All right, so this is let's say this is the 30-yard line. Okay, and so there's. All right, so you posted this on Instagram or whatever. All right, but it says hashtag invisible owner. What? And hashtag where is he? Hashtag the owner. Owner, that is. Alright. What is up with that anyway? Okay. So there's an invisible owner with an invisible leash. Invisible leash. Okay, so invisible owner, invisible leash, giving his dog, or giving the dog a walk. And we want to know, where is the owner? Okay. Well, can we say anything?
Don't we have to know the length of the leash?
You have to know the length of the leash. Okay, so it is invisible, but it's elastic. Okay, the leash is elastic. It can technically stretch very far, but we know something about this dog. The dog doesn't like to stretch too hard against the leash. Okay, and so much so we can say things like about 2/3 of the time, the dog doesn't like to go more than 1 yard away from the owner. Dog, do you know what the next statement is? About 95% of the time, the dog doesn't like to go more than 2 yards from the owner, okay? No more than 2 yards. And only in very, very, very rare circumstances will the dog go more than 3 yards from the owner, okay? So very, very rarely. Okay, so we know this about the dog and the leash, this invisible elastic leash. So based on this, but technically the leash can stretch very far. So what can we say about the location of the owner?
Probably within 2 yards either way, but and almost definitely within 3 yards.
Okay. Alright. So what I have to say is, in truth, I do not know where the owner is, but I can be about 95% confident that the owner is within 2 yards of the dog. Okay? And my dog is unusually huge. But that would put the owner between the 28-yard line and 32-yard line. Okay, if the dog is located at the 30-yard line, then I can say I don't know exactly where the owner is, but I'm 95% confident that the owner is between the 28-yard line and 32-yard line. Does that sound like a fair statement to make? Mm-hmm. Okay, so we do not know exactly where the owner is. Okay, but we can say I am 95% confident the owner is between the 28-yard line and 32-yard line. Okay. Yeah, my dog is like 6 feet, 7 feet long, according to my picture. It's not a good picture, but okay. And I can also change it to say I'm like 2/3 confident, like 68% confident that the owner's within 1 yard of the dog. And I could say I'm very confident, very, very confident that the owner's within 3 yards of the dog. But is the owner guaranteed to be within 3 yards of the dog? No. Okay? It's very possible that the moment this photograph was taken, it's possible that the dog was straining very hard against the leash and happened to pull more than 3 yards away from the owner. Okay? It's possible. Unlikely, but it's possible. Okay. So yeah, what does it mean if the owner happened to be 2.5 yards away from the dog? It means that when you took this picture, it just happened to be one of those rare occasions where the dog was pulling hard against the leash, okay? But we're hoping, okay, when I say a statement like this, I'm 95% confident that the owner's between the 28-yard line and 32-yard line. I'm hoping that this is not one of those bizarro occasions and that this was one of the more mundane 95% of the time occasions where the dog is not pulling that hard against the leash and is within 2 yards of the owner. Okay, so with that in mind, alright, this is supposed to be a parallel story to what we have going on with confidence intervals, okay? In our case, the population mean mu is representative of the owner, okay? This location is set somewhere where we don't know, that we don't know, okay? We can see y bar, we can see the sample mean, okay? And we just studied the properties of the sample mean, or the sampling distribution, and we know that if these conditions are met, then the sampling distribution follows a normal distribution, which means that y bar won't be, 95% of the time y bar is within 2 standard deviations of the mean, okay? So the location of y bar, is kind of like follows the location of the dog. So we can observe y bar, and based on what we know about y bar and the properties of the normal distribution, we can make statements about mu. So mu is analogous. I don't know how to spell it. Now I have anal written on the. Mu is like the owner, and y bar is like the dog. Okay, so we can see y bar, and we know how y bar should behave. Okay, so according to central limit theorem, y bar comes from a normal distribution. Mu equal to mu, and standard deviation equal sigma over the square root of n. Okay? So 95% of the time, y bar should be within 2, technically 1.96 standard deviations of mu. Okay, so we could, or we might, we could say something like, I am 95% confident that mu is within 1.96 standard deviations of y bar. Okay? Or if we want to convert it, we can say standard deviations and y bar plus 1.96 standard deviations. So far, so good. Is that okay? There's a problem we run into though. Can you guys spot the problem? The standard deviation is this, sigma over the square root of n. Okay, do you see the problem now?
We don't know n.
We don't know sigma. We don't know sigma. Okay, we do know n. We do know y bar and s and n, but we have no idea what sigma is. We have no idea what sigma is. So what do we do about that? Okay, so if we go back to the story, it's like, actually I don't quite remember how the leash worked. And it's like, maybe the leash was a little bit looser or a little bit tighter and the dog, you know, so it's like, well, was it 95% of the time the dog doesn't like to go more than 2.2 yards or 1.8, you know, it's something like I don't know the properties of the leash anymore, okay? So we have a problem here, okay? So what we're gonna do is we have no idea what sigma is, so we're gonna do our best guess. We're gonna say, well, the best guess I have for sigma right now is what? The best guess I have for the population standard deviation would be my sample standard deviation, okay? So the best guess I have for the population standard deviation is my sample standard deviation. But again, I don't know if my sample standard deviation is too big or too small. I don't know, okay? So, okay, so I'll write this. Problem. The standard deviation is equal to sigma over the square root of n. But we do not know sigma, okay? So we will use our best guess for sigma, which is s, okay? But we do not know if s is too big or s is too small. So what should we do? Well, we're going to compensate, okay? We're going to change this number. I'm going to say, okay, well, I'll just plug in s. So I'm going to use s over the square root of n instead of sigma over the square root of n. Okay. But to compensate, what should I do? Instead of 1.96, I should use a different number. And should that number be bigger or smaller? Just to be safe.
Bigger.
It should be bigger, okay? So just to be safe, I should make that number bigger. But how much bigger, okay? Well, that's a much more difficult question. And these other people figured that out for us, okay? And they created something called the t-distribution. And, well, in the beginning, they really had no idea how much they needed to compensate. So, to figure this out, the guy who worked on it, he brute forced it, okay? Kind of like we did with the simulation here, except this was back in the early 1900s. So he wrote down numbers on a slip of paper, put it in a can, and he shook them up and he drew them out at random. He calculated the standard deviation of each of these by hand over and over and over again, and created and figured out exactly how much he needs to change this 1.96 by, okay? So it was a lot of hard work, and then later on, the people figured out the theoretic math behind it, and they figured out the actual distribution. But in the beginning, they had no idea, and they did this painstaking procedure, okay? There was a guy at the Guinness factory in Dublin, because he was like quality control. Anyway, so we will not use 1.96, but a larger number. Okay, and that number comes from what we call the t-distribution. And so the way the t-distribution works, alright, the t-distribution depends on your sample size, okay? And it says if you took a big sample, if your sample size is huge, your sample standard deviation is probably pretty close to the population standard deviation, so the amount you need to compensate is going to be little. But if your sample size is small, you're going to have to compensate more because your standard deviation could vary quite a bit more. Okay, so the t-distribution depends on our sample size, and it depends on it in what they call degrees of freedom. It's lowercase t. T-distribution depends on degrees of freedom, or df, okay? And df is equal to n minus 1, okay? Large sample sizes have little, quote, compensation, while smaller sample sizes will have need more compensation. Okay, so we're adjusting this 1.96 to a different number. Conceptually, is this okay? All right, so let's take a look at our t-table, okay? And we will use this t-table quite a bit. It's page 618 in your textbook, or it should be in the page after the normal curve. I'm gonna give you guys. Is this okay? Any questions? Okay, so at the bottom you see critical value for confidence level. Alright, and so just go to that column 95%. Okay, and you can see infinity. So if you have infinity degrees of freedom, meaning your sample size is infinitely large, then you don't need to make any compensation at all because your sample standard deviation would be the population standard deviation. So you use 1.96 directly. Okay, you guys see that? Okay, but then if you have anything less than infinity, which is going to be every single time, you have to compensate a little. So instead of 1.96, the number gets a little bit bigger. Okay, and you can see all the way at the very top, okay, or very close to the top, the amount you compensate by is much larger. Okay, so if you have a sample size of 2, your degrees of freedom is just 1. And instead of 1.96, you're using a ridiculously large 12.7, okay? Which, I mean, maybe just because they're numbers, it doesn't mean a whole lot to you. But if you have to use 12.7 there, it's not going to be incredibly useful, okay? In practicality, okay? And you'll notice we don't have anything for sample size of 1, right? Sample size of 1 would be degrees of freedom 0. And we don't have anything there. Why?
No variation.
Yeah, because if I just draw one person, it tells me nothing about the population. Okay? Because if I draw one person at random, this person could be LeBron James. Okay? Which would tell me nothing. It tells me about LeBron James, but it tells me nothing about the average in the population or anything like that, and I have no idea if this guy is anywhere close to the rest of the world or not. Okay. Whereas, at least with 2, I get an idea, a little bit of an idea of what the variation exists, and as we draw more, we get some more. Okay, so instead of going between y bar plus or minus 1.96 standard deviations, we'll say we can, for a 95% confidence interval, okay, let's say for 95% confidence interval, and let's say our sample size is 10 people, okay, and the mean of my 10 people is let's say 96.3 was the IQ, and the standard deviation was 14.5. Okay, well then I can say I am 95% confident that, and what am I making a statement about? Not the owner of the dog, but the location of the population mean, mu, okay? That mu, the population mean, so not any individuals or anything like that, we're just making a statement about the population mean is between, okay, and I'm going to put y bar plus or minus, and I'm going to put something called t star, okay? T star times s over the square root of n, okay? T star just means a value that I'm going to draw from the t table, okay? A critical value. Table 4 even says critical values of students' t distribution. So I'll split this into 2 parts, okay? So I'll do 96.3 minus t star. So for 95%, if I have a sample size of 10, what's my degrees of freedom? I've got 9 degrees of freedom, so my t star will be 2.262. Now this is as big as I can blow up the table, but there's too many numbers. Times s, which is 14.5, divided by the square root of 10. Okay, and then so that's going to give me a number on the low end, and then I do the same thing. 96.3 plus 2.262 times 14.5 over the square root of 10. And I get so I get 2 numbers, which kind of form the boundaries of where I am confident that mu lies. Oh yeah. Okay. So let's do this. 14.5 divided by the square root of 10 times 2.262. So I get 85.63. Okay, and to 106.97. 95% confident that the population mean mu, so the population mean average IQ score, is between 85.63 and 106.97. Alright, based on my single sample of 10 people's IQ scores. Right? If I had a larger sample, I would have better precision here. Okay? Because my n would increase, so my standard error goes down. Okay? Yeah. S over the square root of n, by the way, is known as the standard error. Okay, so just a theoretical question. If I wanted to be 99% confident about where the population mean mu is, if I want to be 99% confident, what would happen to my interval? Would it get shrink or bigger? I want to be 99% confident. It'd be bigger, okay? Because if I want to be more confident about capturing where mu was, I need to make a wider zone, right? If I want to be really confident about the location of the owner of the invisible dog, I would just say, oh, the owner is somewhere on that football field, okay? But if we try to be, but if I want to be like 100% confident, okay, or something ridiculously large, well, I can be 100% confident. I just have to say the number somewhere between negative infinity and positive infinity, okay? But that's not useful. If we try to be too confident, our interval gets too wide, and I would say even an interval like from 85 to 107, that's pretty wide, okay? So we can decrease the width to kind of get a more narrow range at the trade-off of reducing the amount of confidence we have. And again, this is a statement of confidence. We are not saying, okay, I should write, do not say there is a 95% chance that mu is between blank and blank. Chance or probability or whatever word to express that idea. Why would I not want to use that? Why would I not want to say there's a 95% probability that mu is between such number and such number? Do we have time for this silly illustration here? Alright. I'm going to grab a coin out of here. Okay. And you say, if I flip this, what's the probability that it lands heads?
50%.
50%. Okay. Oops. It fell. Alright. Okay, so now that I flipped it, okay, what's the probability that it has landed heads? 50%. Okay. What's the probability that it lands heads? Or it has landed heads or whatever? 0. Okay. Yeah. So the question of probability only makes sense for events of uncertainty. Okay? Once it has flipped and once it has landed, there's no more uncertainty about it. Okay? It doesn't make sense to say there's a 50% probability that it has landed heads. Okay? You guys don't know what it is. All right? So you can only say, I'm 50% confident that it has landed heads, or I'm 50% confident that it hasn't landed heads, or something. Okay? But there's no probability associated with this because it is determined. Okay? And the way this works, we're treating mu, the population mean, as a fixed value. This is a property of the population. There's no uncertainty about it. Okay? The only thing that's uncertain and random is the sample we draw and the sample mean that we observe. but the actual mean mu of the population, there's no uncertainty about it. So it doesn't make sense to say there's some probability about where the location is. It's either in this interval or it's not. Okay, it doesn't care what our interval looks like. It's set somewhere. So we don't know where it is, so we can only express something about its, about our confidence about where it is, based on what we've observed, but there's no uncertainty about it, okay? The coin landed heads, by the way. Okay, so no uncertainty about the location of mu. Okay, it's just unknown to us. Alright. And so, we can say I'm 95% confident that it's in between these two values, but the truth is it could be outside of that range, and that just means the sample you observed happened to be one of those rare occasions where your sample mean ended up far away from the population. Yes?
Is there any value in statistics for finding the mean between the two boundaries that you kind of like finding the average and then using that as a working mean or a working mean?
Like
I want to, since you say I'm 95% confident that it's between 85.63 and 106.97. If you found the average of those two numbers.
The average of those two numbers would be 96.3. Would be your sample mean.
Right. Okay. That makes sense.
Because that serves as the center point, right? This is your best guess for the population mean, and we're just going out kind of this the length of the leash to guess where the mu might be. Is there some value in using this? Sure. You can say, well, I have no idea what the mean mu is. My best guess for it right now is 96.3, okay? And you can go on with your life. You just have to be aware that this could be wrong, okay? Or it's very likely, it's almost certain that this is not the exact value of mu, and it's just, well, how much does that matter? If it's pretty close, maybe it doesn't matter. If it's far away, you know, that could make serious things. Okay, we'll stop there.